When you send Bitcoin to someone's address, you're not sending it to a person, you're locking it behind a tiny program. Today, we'll dissect Bitcoin's two foundational locking scripts, P2PKH and Bear Multisig, and we'll uncover a 14-year-old bug baked into every multisig spend that the network is now stuck with forever. Start with the legacy default, P2PKH hash or P2PKH. When you pay Bob's address, you create a UTXO, an unspent transaction output, locked by a short script. The address itself is a commitment. It contains the hash of Bob's public key, not the key itself. To spend, Bob must reveal the original public key and produce a valid signature. The lockbox checks that his key hashes to the committed value, then verifies his signature. Two scripts work together. The output script, also called the scriptPubKey, sets the lock, opdub, op hash 1.city. The committed key hash, op equal verify, op CHECKSIG. The input script, or scriptSig, provides the key, the signature, then the public key. An opcode is just a single instruction in Bitcoin's stack-based language. To validate, the network concatenates input plus output and runs it on a stack. If the stack ends with true, the spend is authorized. Walk-through execution. First, push the signature onto the stack, then push the public key. Stack now holds signature, then pub key on top. Opdub duplicates the top item, so we have signature, pubkey. Op hash 160 pops the top pub key and replaces it with its hash. Stack, signature, pubkey, hash of pubkey. Now push the committed key hash from the output script. Op equal verify pops the two top items, the computed hash and the committed hash, and checks they match. If they don't, the script aborts. If they do, both are consumed and we're left with signature and pub key. Finally, op CHECKSIG pops both, verifies the signature against the public key over the transaction data, and pushes true. The spend is valid. Notice the elegance. The spender proves they own the preimage of the hash and proves they hold the matching private key in one tight sequence. The insight is worth stating directly. A Bitcoin address does not contain a public key, it contains a hash. The key stays hidden until the moment of spending, which provides a small privacy benefit and a quantum resistance buffer for unspent coins. P2PKH locks funds to one party, controlled by one key. But what if you need several parties to agree before funds can move? Multisignature generalizes this. A T of K multisig output requires T-valid signatures out of K-listed public keys. Take the canonical 2 of 3. 3 keys A, B, C, any two must sign. The output script reads 2, then keys A, B, C, then 3, then OP CHECKMULTISIG. The leading 2 is the threshold, the trailing 3 is the key count. The input script provides the signatures, but with a strange prefix. It begins with OP0, then the two signatures. Watch what happens when CHECKMULTISIG executes. Build the stack, input pushes OP0, SIG A, SIG B. Output pushes 2, then A, B, C, then 3. The full stack reads from bottom to top, dummy 0, SIG A, SIG B, 2, A, B, C, 3. Now OP CHECKMULTISIG fires. It pops the top number 3, telling it how many public keys follow. It pops 3 keys. C, B, A, it pops the next number, 2, the signature count. It pops 2 signatures. SIG B, SIG A. It checks them against the keys and then pops one more item. That extra pop is the dummy. Without OP0 sitting at the bottom, the stack underflows and the script fails. The signatures could be perfectly valid and the spend still wouldn't work. So every multisig input script begins with OP0, purely to feed that final, unexplained pop. One quick clarification. Bare multisig used directly as an output, is policy limited to 3 keys total. That's a relay rule, not a consensus rule. Wrap the same script inside P2 script hash and you get 15 keys. P2WSH and P2TR push that to 20. The 3-key ceiling is specific to bare multisig, not to multisig itself. Why the dummy? The leading theory points to inefficiency. Consider 1 of 5. One signature must match 1 of 5 keys. CHECKMULTISIG tries them in order. If only key 4 matches, it runs 5 signature checks for a single signature. Wasteful. The dummy element could have been repurposed by a future soft fork, a backwards compatible rule tightening, to encode an index map telling the verifier which key matches which signature. The upgrade never came. In 2017, BIP 147 ossified the rule. The dummy must be exactly OP0. The future feature is now permanently blocked. P2PKH and bare multisig encode 2 paradigms: single-party control via hash commitment and multi-party control via threshold signatures. Modern wrappers, P2SH, P2WSH, P2TR, have largely replaced them, but the conceptual blueprint remains. And every multisig span still begins with a placeholder for a feature that never shipped.